The topic of today's lecture is moment of a couple. As such, the objectives are to define a couple and determine the moment of a couple. Activities associated with that would be a reading quiz, applications, moment of a couple, concept quiz, group problem solving, and an attention quiz. So let's get started. In statics, a couple is defined as blank separated by a perpendicular distance. In statics, a couple is defined as two forces of equal magnitude acting in opposite direction separated by a perpendicular distance. So the correct answer is D. Number 2, the moment of a couple is called a what? Blank vector. So the moment of a couple is called a free vector. Okay? Not a spin or romantic or sliding vector. It's called a free vector. So let's take a look at some applications. Here's a best example of a couple that's applied as such to turn this wheel. Okay. There could be both 30 Newton as such, it's shown here on this figure. They could be 40 Newton as shown on this figure. The distances could be separated depending on where the location of the applied couple would be. In this case, as you can see, the hand is further out here, so the distance is 0.4 meter. In this case, the distances are closer together. The hands are closer together. The distance would be shortened by 0.1 meter at 0.3 meters. So a torque or moment of 12 Newton is required to rotate this wheel. Why does one of the two grips of the wheel above requires less force to rotate the wheel? And that is because of the distance that is associated with that. The one that hands are closer and the distance is shorter and it requires more force. Another example, again, could be a steering wheel. This is a lift truck. When you grip a vehicle's steering wheel with both hands, a couple moment is applied to the wheel. They are acting roughly in the same magnitude, but in opposite direction along the same line of action. Would older vehicles without power steering have larger or smaller steering wheels? They have larger steering wheels. A couple is defined as two parallel forces with the same magnitude but opposite in direction, separated by a perpendicular distance. Again, as shown on this figure, as you can see here, and they are of the same magnitude, separated by the same by a distance. The first things that comes into mind of most people is, and this is a common mistake when they deal with calculating the couple, and that is they simply multiply that by 2, assuming since there is one F acting counterclockwise, the other one is also acting counterclockwise. It's going to double the force. We try to have a much better understanding of what a moment would be due to a couple. But remember that these couple, there are two forces acting in the opposite direction, but they are separated by a perpendicular distance, d. So the moment of a couple is defined as simply F times d. So do not double that and saying there'll be a force, there'll be a moment F times d because of F, and there will be another moment because of the negative F. That's a common mistake that learners would make when they're dealing with the couple at the beginning. So it's simply F D for a scalar analysis, or as with the vector analysis, we use the cross product R cross F. So R is a position vector from the line of action of minus F to the line of action of F. So please keep that in mind. So again, the net force equals 0, and the magnitude of the net moment equals F times D. This is the net external effect of a couple. The moment of a couple depends on the distance between the forces, and as such, the moment of a couple is a free vector. As shown, it can be really moved anywhere on the body and have the same external effect on the body as shown. Okay. So we use the same rules to add moments to couples. We use the same rule as adding any vector. Okay. So please make sure you guys keep that in mind. Okay. So let's take a look at an example in a scalar approach in calculating what needs to be calculated. Okay. All right. So two couples act on a beam with the geometry shown is given. 300 pounds, kind of like downward angle, upward angle to the left, and these two. So this is one couple as shown here, and this is the other couple as shown here. So we would like to find the resultant couple. The plan should be we're going to resolve the forces in x and y directions so they can be treated as couples. Then we would add two couples to find the resultant couple. So now let's take a look at it. The x and y component of the upper left, the 300 pounds here, are 4/5 of 300 and 3/5. One would be vertically up, and the other one would be vertical to the left. Okay. Then the question is, do both of these components form couples with their matching component of the other 300 pound force? No, they're not. Only the 240 pound component create a couple. And why is that? Because as you can see, this force is also would be pretty much resolved into two. These two would pretty much, these two components, they go along the same line. They don't really create any couple. They just cancel each other out. It's these two components that I marked by X for the same couple that are 2 feet apart that would actually contribute to the moment for that particular couple. So it's very important to keep in that mind. Now, what about the 150 pound? We would resolve that into its appropriate components. Again, one component downward for that one. And again, the couple would be due to the X component. So all we need to do is really calculate that. So the net moment is equal to obviously the appropriate components multiplied by the distance. Again, we're taking the sum of the moment. We don't take it about any axis or any point. We just take the sum of the moments. So make sure that is perfectly clear for you in this case. Minus 240 times 2, minus 150 pounds cosine 32. This is for this component. This is the X component. Remember, only this component of the force is going to create a couple. The component that goes along the line of AB doesn't contribute to creating any moment since they cancel each other out, as I've just shown you. So the final answer would be minus 739.8. And that makes sense because also the force in this way, the couple, as you can see, this would turn the system this way, and this would also turn our system this way. So since the positive is supposed to be counterclockwise, we add the two negatives, assume in this case a clockwise, so the answer must be a negative number. Let's use a vector approach to do the same thing before we get into our concept quiz. Given A is 35 Newton force couple acting on the rod as shown, okay, and directions are also shown. A couple moment acting on the rod in Cartesian vector notation is what we would like to find. The plan is we're going to use a cross product, R cross F. Then we would set R as the R sub AB and F as 35, and we would calculate the cross product to find M. Let's get to it. R sub AB, 0I minus 0.25J plus 0.25 tangent of 30K. This is R sub AB. The position vector goes from A to B. As such, we do the multiplication. This would drop out, and we would end up with this equation up here. F would be I 0I 0J 35K. Again, note that both of the components, I and J components, are 0. We would do a cross product, R sub AB times F. As such, IJK. This is the way we been doing it for the cross product. And this is for the R sub AB. This is the I component, J component, K component. And this is for IJK. This is actually for the force. As such, we take the determinant of this matrix, and many of the terms turn out to be 0. So the end result would be that. Okay, let's take a look at a conceptual quiz before we can move on. Okay. So F1 and F2 form a couple. The moment of a couple is given by blank. What? And it's pretty important to be able to solve this problem at this stage. So F1 and F2 form a couple. The moment of the couple is given by which one of these cross products that are given here. In this case, the correct answer is R2 cross F1. And if you take a look at the figure, you should be able to determine that. And we have force F1 in this case, and we have force F2. Again, in order for us to, remember it's a free vector, so in order for us to calculate that, really we need to go from, we need to use R2 to cross it with F1 to be able to calculate that. Secondly, if three couples act on a body, the overall result is that the net force is not equal to 0. That's A. Answer B, the net force and net moments are equal to 0. Remember, it's a couple acting on a body. The net moment equals 0, but the net force is not necessarily equal to 0. The net force equals 0, but the net moment is not necessarily equal to 0. Just by definition, answer D is the correct answer, okay? Let's move on. A group problem solving, scalar approach. There is such a problem given. So let's use a scalar approach for this problem. Then there would be a vector approach coming after that, and then we would have our attention quiz and wrap this up. So two couples act on the beam. The resultant couple is 0, as you can see here. The magnitudes of the forces P and F and the distance D is to be determined. So we need to look for the magnitude of both P and F and the distance between them. Okay. So use the definition of a scalar couple to find P and F. We would determine the net moment, and then we would equate the net moment to 0 to find C. Let's get to it. From the definition of a couple, P is 2 kilonewton and F is 4 kilonewton. Knowing this 4 up here, I should be able to find that. And since they're a couple, if this force here is 2 kilonewton, and this would be 2. Now determine the net moment. Summation of moment is 2 times 0.3 minus 4 times d. We equate that to 0. As such, we can easily calculate d, as you can see. Okay. Let's look at another problem using a vector approach. F is given as 15k Newton, and minus F is given as minus 15k Newton. There are a couple. We're going to find a couple moment acting on the pipe assembly using the Cartesian vector notation. So you know that we can use two approaches by now, right? One is the approach that we just used, and the other one is the vector approach. So we would find the cross R cross F, that would be the M. Then we would set R as our position vector, R sub AB, and F as 15 Newton, and we would calculate the cross product to find the M. So let's see, the position vector R sub AB is shown as such. The good news is this component would drop out. The less components we have to deal with, the better it is, the easier the calculations would be. F is also given. We set the cross product matrix IJK, and we would just calculate the determinant of that, and that would be the M 7.I minus 15J Newton meter. Let's take a look at an attention quiz. Okay, so a couple is applied to the beam as shown. The key here is that this is a couple. Its moment equal to, again, what's the shortest distance in this case? They're not perpendicular to each other, and we would like to find that. The correct answer is 60. As you can see here, again, it's a couple, 50 Newton. We would find the component of this direction. We would find the component of that in the other direction. We simply multiply it by 2, and this would be 30. Okay, and we simply multiply that by 2. The answer would be 60. And you can determine the couple moment as M is R cross F. If F is minus 20 pounds, the way it is shown here, then what would be the R? We set up the matrix, the correct answer. Then what is R? Is it R sub BC? This is not the answer. R sub CB, that's not the answer. Between R sub AB and R sub BA, we need to decide. In this case, it is going to be R sub BA. Done so many problems like that. Again, we are crossing R by F. F is a couple. Again, we're replacing the force by a couple in this case. So nothing else has changed. So it's going to be R from B. The position vector would be R from B to A. This is point B here, in case it's not that clear, and this is point A. So it's going to be B to A, okay, from positive to negative. So that'd be the position vector R sub B A. Okay, that brings me to the end of today's lecture. The learning continue. If you have questions.